Okay, so let's have a look at problem 668, Kth smallest number in multiplication table. So here we are going to practice the idea of binary search again. So first we'll walk through the statement of the problem, and then we will explain the method and explain how to transform this problem to be a binary search problem. And finally, we share the code and do a rough time complexity analysis. So let's look at the problem statement. So first paragraph, it introduced the familiar multiplication table. So the multiplication table of size m and n is an integer matrix called mat. So where matrix ij equals I times j. So in other words, if we use one-indexed indexing, then the matrix ij element is nothing but the product of its index in row and column. So the question asks, given three integers m and n, so m and n are the table rows and table columns, and k, what we want to return is the kth smallest element in the m by n multiplication table. So here is an example. In example 1, m and n equals 3 and k equals 5. So this is the 3 by 3 table, and k equals 5. If we were to sort this table, and then we can get the fifth element is 3, right? Kth smallest, the fifth smallest. So in example 2, this 2 times 3 table, so we have 6 elements altogether, so the largest one, so that because k equals 6 is 6, so we return 6 in this problem. So here the constraint is that m and n is greater or equal than 1 and less or equal than 3 times 10 to the power 4. So and k is greater or equal than 1 and as it should be, and less or equal than m times n, because we have m times n numbers in total. So but this row and column can be very large. So if m and n are at this bound, then basically m times n roughly is controlled by 9 times 10 to the power 8th. So it's a large number, so we cannot purely use brute force. So with that said, let's look at the method we're going to use. So here the method again is binary search as our previous practices. So the procedure is as follows. First, we define a boolean function to produce order and monotonicity. So this actually enables us to use a binary search. So that's actually an important part. And also for most of the problem, once we are able to define the boolean function, then the second step basically are natural, because we can usually find the search space easily according to the problem, and then so we can do the shrinkage according to the interpretation of the boolean function. So that's the second step. So to recap, so based on the boolean function, we transform the problem to a optimization problem, either maximization or minimization, because of the order or monotonicity in step 1. So we have these two possibilities, and then we do the shrinkage on proper search space. So for example, this problem, at the very first thing, we may not think of binary search. Actually, if we practice a number of this problem, so we can actually have a feeling at the very beginning this is a standard binary search idea. So here, in order to make it clear at the very beginning, we'll first state the formulation of the problem, the reformulation. So actually during the coding part, so we can gradually grasp the idea. So first we will define the fulfill function. That is the boolean function in step 1. So the function returns if there are at least k elements in the multiplication table that are less or equal than number. Then what the problem desires actually is minimal of such a number, right, in this argument. So that's the reformulation of the problem. So here, before we write code, I want to first make a note. So here we transform the problem to a minimization problem, right? So we write the fulfill function by considering the row-wise count increments. That's what I want to write. So that's one version of the fulfill function. So the challenge for this video is that can you write a version of the fulfill function by considering column-wise count increments? So actually I did both the two versions of the increment of the boolean function to produce monotonicity. So that's actually the fun part of using the binary search. So with the method, procedure, reformulation, and challenge covered, let's look at the problem and the coding. First, as we stated that, so we define the boolean function. So for this, again, I'll just call it fulfill. So we will initialize a number. So basically, this function will return whether there are at least k elements. K is the key here in the multi table, such that they are less or equal than this number. So then, for this purpose, I'm going to initialize a count, which I will count this with respect to k, compare with k. So then, basically, a iteration. So for value in range. So because we start from 1, so then we end at m. So m plus 1 here. So we want to examine the row with index value and to see if we can add the whole row or a part of the row, right? The thing is like this. So if we check, we can add the whole row. So in other words, if this one times n, the largest column index, is less or equal than none, so we can add the whole row. Add the whole row. That is n elements, right? So this is the one case. Otherwise, so we cannot. If value times n is larger than none, we can only add part of that. We can only add k elements. The k is such that k times this value is less or equal than none, right? So basically, k will be the integer part of num divided by value, right? That's what we have. So still another case. So if value itself, for example, if value itself is that greater than the number, because the row index is too large, so we cannot add any elements. We cannot add elements at all. So in other words, we cannot increment the count. So summarize the first two cases and the third one. What we want to add is that the minimum of num divided by value. So if we cannot add the whole row, we will add this amount of elements. Otherwise, we add the whole row. So overall, we need to add the minimal of these two. So this is the increment, right? So if add equals 0, so in other words, we cannot add any more, or it's too large, just break. So otherwise, we just need to increment the count by this amount, right? So finally, we are going to compare this count with respect to k. So because we want to see if there are the count is the number in the table, so that's less or equal than number. So we want to see if this count is greater or equal than k, right? So that's the function. So if we inspect that, we iterate from the row indices, right? So we are write the fulfill function by considering row-wise count increments. So again, let me remind you the challenge. Could you write a version of the fulfill by considering column-wise count increments? That's also similar, but it's sort of routine. It's different sorts of procedure, I would say. So that's the first step. Now look at the second step, do binary search in a proper search space. So for this problem, first we have transformed this problem to be this. Find min x such that fulfill x is true, right? So you can interpret this x as none if we like. So now we need to determine the search scope. So here let's come back to the constraint which plays the role. Here k is greater or equal than 1, less or equal than m times n. That basically gives us the lower bound and upper bound. Basically the lower bound will be 1 and the upper bound will be m times n. So I will call it left and right, just to make an analogy with the vanilla binary search. So with that said, let's do the procedure. So then first I will initialize this L and R to be 1 and m times n. Then what we want to do is that, well, L is less than R. So this is a routine now. So we want to check mid. So mid will be half of the range. But if we use left as reference point, then this will be R minus L, then divided by 2. Here is integer division. So up to now, so we set the temporary variable mid. So then we do the shrinkage. So we check if fulfill mid is true. So if it's true, it means that there are key numbers less or equal than mid. So if it is true, then actually we can shrink our search space. So from lower or left to mid. And mid is included because mid is true, right? So we reset the right to mid. So otherwise, fulfill will return false. Then it said that, oh, this mid is too small. We need to increase. We need to search in the other direction. That is strictly larger than mid. So that is mid plus 1 to the upper. So we set the left equals mid plus 1. Then if we interpret the problem, what we want to return should be L. So that's basically a solution to this problem. So let's check for a special case. So this passes the first example. Now let's look at the second example. That is 236. So the 236 one is sort of edge case or trivial. So we have this passed. So now let's check the generic case. So it passes the generic case. So with that said, let me do a quick term complexity analysis. Then basically that's about it. So for this, so we know that the main thing is here. So the left and the right is from 1 to m minus n. The search range is that m times n minus 1. So roughly m times n. So right. So this is the search range. So because we're doing binary shrinkage, we're calling this procedure log 2 times m times n times. So that's the thing. So each time we call the fulfill function. But the fulfill function is a linear procedure, and it has term complexity equal this number, right? So this number, so this is O of M. So actually it's yeah, so it's let's see if it's M or yeah. So here is M, right? Because we count row wise. So if we do count by column wise, that is O of N, right? So that's basically roughly the term complexity. But if we like, we can make it more precise. For example, here is log 2, M times N is M is like this, times 10 to the power 4. Then times this again, so it's times 3 times 10 to the power 4, right? Then times a 10 to the power 3, it's 3 times 10 to the power 4, right? So actually we can break the log. So basically it's log 2, that is 9 times 10 to the power 8, right? So that's times 3 times 10 to the power 4. So what we get is that it equals log 2 9 plus log 2 10 to the power 8. So then times the tail, times 3 times 10 to the power 4, right? So but this one is less or equal, so I will use this is less or equal than 4, right? So the first one, and the second one is less or equal than 8 times log 210 is also less than 4, so it's times 4. Then we have times 3 times 10 to the power 4. So right, so roughly, so this order of 10 to the power 4th. If you multiply them as 10 to the power 5th, that's basically a very rough estimate. So I guess, but the idea is just a rough estimate. So yeah, with that said, I guess that's about it for this problem. Thank you very much.